All right, well, welcome everyone to today's workshop where we'll be talking about machine learning in practice. And so this workshop is going to focus on using R and Python to implement machine learning and using the best practices around machine learning in these frameworks. So last time we talked about an introduction to machine learning, where we talked about the basic steps of performing machine learning using the UI of H2O. Today, we're going to get more into the coding with R and Python. So as we said before, we tend to start with the problem definition, if you're lucky, or sometimes you just get some data dropped into your lap, at which point you would form your problem that you wanted to solve. And then you tend to go and do a little bit of data exploration. So you look at the data, you do some visualizations, and you try to understand your data and provide yourself intuition on what is going on with the data set. And this helps a lot when you actually get into the modeling. After you generate models, sometimes there's things that kind of go wrong or are strange, or you want to improve your model performance. And sometimes the intuition that you've built during this data exploration phase can really help you to generate ideas around solving or improving performance in your model. Then once we have a good idea of the model and we have our intuition built, we go into this iterative cycle of training the model. So this tends to start with feature engineering, where you look at your predictors and your data and also your outcomes, and you transform them into something that would be good for modeling. You also then go on to the actual modeling. So you start to choose a model and find out the best hyperparameters, estimate the performance, and then you go on into assess. And so this is a very cyclical procedure where you're trying to improve your model until it gets to a point that it's able to be deployed. So let's talk about what this cycle means or looks like practically. So this is a very old slide from a long time ago, when this was kind of a statement on how the previous diagram could be broken down. So again, same thing, problem formulation. You figure out what it is that you need to do and make sure that you have the data to do it. Then you have a separate step of data processing where you clean, transform, filter, aggregate, and impute. So these are kind of feature engineering kind of tasks, especially the aggregation and imputing part. And then you can split your data set into your predictors, which would be X, and then your outcome variables or your response variables, which would be Y. So now you've done all this work on your data, right? It's all ready, perfect. And now you go and train your models and you evaluate them. So the reason that this slide is old, I don't think it's even on their website anymore, is because there's a different strategy for kind of approaching this. And there are some issues in the separation of these two steps with the data processing and machine learning. Today, we're going to try to talk about what those issues are and also how we can make sure that we implement these in the best way possible. All right, so before we even get to that, tell me about your experience with machine learning. And when you try to train models, what are some common steps, or what are the steps that you tend to take whenever you train your models? And you could give the general breakdown, or you could just give just some things that you do.
What one one very important step is to kind of decide on the type of model you want to use.
Oh, I like that. Yeah. So identify what might be a good model, because that will influence what you need to do even in the pre-processing to the data. That's a good point. And it also influences what you will be able to kind of do with your model. So for example, if you use one type of model, it might be highly interpretable. You can look at coefficients, you can look at different type of breakdowns, and it like makes complete sense. Other type of models are super opaque. So that's a really good point. I like that. Any other thoughts?
Adrian says, split the data into training and test sets.
Oh, what a good point. I love that you just brought that up. That's a really good part as well, because that helps us to understand how the model generalizes. And what does that mean? What does that mean? It means how, after you're done training the model, how does it perform on data that is never seen before in its life? So that is an excellent point. Wow. Any other thoughts? I see. Feature engineering, transformations, or other pre-processing. I love that statement, especially because we're talking about training the model. It seems as if the suggestion is that feature engineering and transformations and other pre-processing occur with the training of the model. So I really love that point. That's a great point, and we're going to discuss that at length. Any other thoughts? Well, honestly, you pretty much got the ones that I was going to say. So let's just chat about what a general outline might look like. So first, one may be inclined, as someone said, to first split your data into the training and testing set. So this is data for training, and a phrase that is used, especially by Jesse, to understand what the test set is the golden holdout set. And think about it as that. Like, this is something that you will use at the very last to understand the performance and the generalization capabilities of your model. Like, you don't just want to be casually using this here and there at the end of a training part. This is the end, the super end, the golden end. Okay, so just keep that in mind. So after you have split your data into the train and golden holdout set, then you might think about training your model using cross-validation, because at that point you would actually only have the training set. So how would you best use this data that you have to be able to understand the generalization capabilities of your model? Well, you could use cross-validation. And what is cross-validation? So the way that I think about cross-validation is you take the training data that you have and you split it up into now a sub-training set and a sub-testing set. And you might do this one or more times so you can iterate and repeat this process to understand how your model performs on different subsets of the data. So a term that is often used or is popularly used for the subsets during cross-validation is the part that would be the training set is called the analysis set. And the part that would be called the test set is called the assessment set. So this kind of distinguishes what is the training and testing set versus like the sub testing sets and training sets of cross-validation. And again, we like to do cross-validation because it gives us an estimate on model performance without having to go to the test data. So we repeat the splitting of the data randomly or otherwise, and we'll talk about some different ways that you can do this resampling of your training data. And we look at the performance of the model on these separate assessment sets. So this is one step that you might do. And again, this is going to help you to understand the performance of your model, as well as any hyperparameters that you might have built in. And so speaking of hyperparameters, let's talk specifically about that. So with cross-validation, you also might want to do hyperparameter tuning if your model requires that. So during cross-validation, you would actually test out each hyperparameter set. Okay, so what is this hyperparameter? This hyperparameter is something, one or more hyperparameters, that cannot be actually like calculated. It's something that you kind of have to test and try out to see if it performs well. And so there are a number of hyperparameter values within models sometimes. And looking at these different hyperparameters can produce different kind of performance in your model. Now, there is a question about how much improvement will be created by hyperparameter tuning, and there's a balance with the time that it takes to do hyperparameter tuning. So whenever you first start your modeling process, you might think about just starting with cross-validation to see if your model learns at all. And then when you find that it has some relatively okay performance, you might go into hyperparameter tuning to try to figure out what would be the hyperparameters or the specific model that would allow you to have the best performance. So again, we do hyperparameter tuning. What we think about hyperparameter tuning is just a bunch of different models. So if you have a random forest and you're tuning something like mtry or the number of trees, you might not think about that as these different hyperparameters of a random forest, but different random forest models altogether. And so in thinking about it that way, that can help you see what you're doing when you combine that with cross-validation. Each new model that you're looking at will go through this cross-validation set. And at the end, it would make sense to be able to compare them. And so this is what cross-validation is going to allow you to do with hyperparameter tuning. All right, so where are we again? Let's just recap. So we split into train and test. We've decided or not to do hyperparameter tuning along with cross-validation. We may have established the best model that we want from the hyperparameters. Then what? So then once we have our cross-validated model, all we actually have are a set of models that are built on subsets of the data, of the training data. So what we want to do actually is build this model on the entire training data, because we already have an estimate of the performance from cross-validation. So now we'll retrain this model that we've selected on the entire training set. And we'll do this thing called backtesting. Now I wrote backtesting here because I just tend to call it that. What I really mean is we're just going to predict on the training set. So, we have a study guide that our teacher gives us. We learn everything that's in the study guide. When we get to the test day, she just gives us the study guide and we see how we do. So if we learn from the study guide, we do super, super well. If we learn nothing from the study guide, we do super, super poorly on the test. And so this is applicable here because this is what gives you intuition about whether your models are going to be able to learn the data, like learn or build from the data. So if your model is failing on the back testing or on the re-predicting the training set, you might want to think about some other alternatives, including adding more features, maybe engineered features, doing different types of transforms on the data, or choosing some different ones. All right, so now we have an estimate of how our model performs. What after that? So after so this is coming like after this bullet point, but this set of things here, so this cross-validation, hyperparameter tuning, retraining the model, and backtesting, this is a large phase that is very, very iterative, okay? So it's not like you just get this one model, hyperparameter tuning, cross-validation, test set. No, you train a lot of different models, compare all of their performances, and when you are finally done and you're finally set, your heart is set on one or two if you have to, then you go and test on the test set, the golden holdout set. Once you see that that's fine, some people, and it depends how you're actually going to be using this test set, you can retrain the model using your hyperparameters on the whole entire data set, so including the test set. And then this is the one that you might think about deploying. Now, it also, again, it does depend on what you intend to do with this test set and whether you'll be able to get new data or what you're really thinking about with this. But this is a step that you can take and then use this model. You can also use the model that's trained on the training set. All right, so what questions do you have about this? And also, by the way, I like this other comment from Adrian about determining if interactions are needed. So I love that point so much because it fits so well into this iterative framework where you would be thinking about what should go into your model. So I really like that. That's a great point. All right, well, let's just ease a little bit further into each one of these steps. Let's see, let's assess, okay? So let's start with this one, the splitting the data into the training and the golden holdout set. So it seems pretty simple, split data, move on. However, there could be some consternation here, okay? So let's say that we have the sample data. This is the world's smallest data set. It does come from a bigger data set, but we're just gonna look at this small bit of it here and we're just gonna think of this as the entire data set, okay? So we're gonna split the data, okay? However, before we split the data, we notice that there's this particular column here, const cost, okay? and you're looking at it and you're like, oh, wow, like I really need, cost to have, good data in it. Like I don't want to drop the ones that have the NaN, like I'd rather fill them in. And, I'm thinking about using this model that requires normalized variables for numerical variables. So I need to do something with this column. So you say to yourself, no problem. I know what to do. I'm going to use some form of imputation to fill in these NAs with some value. And then after I'm done doing that, I'm just going to normalize this column and move on. Right. That sounds like a great plan. The question becomes, when do you do this? Okay, it's a question. So I'm going to let y'all vote. Y'all are going to tell me when we're going to do this. So again, we're just going to use the reactions at the bottom of your Zoom window. Hopefully these arrows are actually here. I think this is speed up and slow down. Anyways, we're going to go backwards arrow. If you think that we would do the imputation and the normalization during the data cleaning and feature engineering, so that would be prior to when we actually got into our modeling process. Or we might split the data first and then compute the NAs and normalization using only the training data. So these are two options. And the last option is, why are you asking me this? It's making me nervous. So go ahead and use that reactions tab here. I think you can find these all under this reaction button. So go ahead and cast your vote. I love suspicious people. All right. So we've got 6 for this right arrow after the initial split. We have 1 for the data cleaning, and we have 3 suspicious people. I love that. I always love to add that option. All right, well, let's figure it out. Let's assess the impact of our actions, okay? So we're just gonna think about what would happen. If I could just make my slide set go forward, that would just be awesome. Okay, so we're gonna assess, we're gonna consider. So what if we split this data after we impute? So this says if we impute and normalize during this feature engineering phase before we even get to the modeling. Now, do recall that the whole point of this is to be able to provide accurate predictions on data that we have never seen. Okay, so let's see what happens. So we decide that we're going to calculate the mean of this column or whatever value that we find to be important, maybe the median, whatever, however we want to do our imputation. We calculate some value. Okay, we calculate that value. We fill in the NaNs of our entire training set. All right, so think about this. If we do mean imputation or something like that, if we do median imputation, the mean and the median require the entirety of this data set to calculate its value. Okay, so we've replaced these values with the mean of the entirety of this column. Then we go on to our normalization, where we do some type of scaling and centering. We need to determine the center. So now we calculate the center value from this old column. We calculate whatever scaling we're going to do if we need the data for that. So like if it's a standard deviation, we again need all the values from this whole column. So we have seen every single value in this entire column. All right, so then we go on and we split the data. All right. So this has the same values, but just in your eyes, in your mind's eye. Just remember that these have been imputed. These NaNs have been imputed using the entire data set. And we have also performed some centering and scaling. Okay. So now we're splitting the data. We have this blue box, which is going to be the training set. We have this red box, which is going to be the testing set. As normal, we train our model using this training set, and we go and we test the performance on our test set. Great. That sounds super normal, and it sounds like mentally fine. But let's look a little bit deeper. So the problem here is in the test set for these 3 values. And the problem is that this data here is actually not unseen. So what does that mean? So it has been seen while you have been doing your feature engineering step and used in the calculations for your models. So again, this X bar that you calculated to fill in the NAs was calculated using this and this. That X bar again that you use to center the data, calculated from including this and this. Standard deviation, use these values to determine the spread. And now, once you decide to put a model to it, so let's say that you do a linear regression, the coefficient of this particular column is based on your imputed, scaled, and centered values. So it has been calculated based on the test set already. So now when you go to predict and you evaluate the performance on the test set, it actually doesn't fully represent the performance of the model on unseen data because it has seen this data. So it could be a little bit optimistic and not give you a realistic result of how you can expect performance to be once you get it into deployment or when you decide to use it. Because whenever you deploy your model would have never been able to see the data that's coming in. So I submit my data to your, I don't know, you're trying to calculate the number of permits for Nashville. You would have never seen my construction cost. You would have never seen this other construction cost. And so you would have no idea how to factor that into the mean or standard deviation for this column. So what do we do then? Well, what's the best approach? So people voted on this and I think they have that down. Essentially what we do is we take just a small change. So we just do our initial split first. Again, we're blue boxing the training set, red boxing the testing set. We're just calculating these values here, this imputation and the scaling and centering from these values only, which is all that the model would have before deployment. We train the model on this, but afterwards, we take these values that we have calculated from the training set, we apply them to the testing set, and then we test the performance. And this will allow us to kind of silo the information that we use during training from the information that we use during testing and have a better estimate of how the model will perform on unseen data. Okay, so that kind of resolves that. All right, that's sounding good. So just to recap, whoever voted for after the initial split, using the training data, that's when we want to do our imputation and normalization. Y'all had it. Nice job. Also, the suspicious people, also right. Okay, so now we've talked about when to split the data, right? When to do the initial split, when we have features that kind of need some engineering. Okay, when we said we want to do it after splitting, right? So now let's go on to the second step, right? So let's talk about cross-validation. So here, actually, one may consider that we may have the same problem, right? So we find that we need to split the data into these subsets. So let's say we're doing something like k-fold cross-validation. That basically means you subset your data, training data, into k different folds. So let's say that's 5. We take the first 4, we train on those, and we now test on that last one. And we do that, leaving the testing set out for each of the folds, okay? Now, we just talked about what it means to split the data and when we should do our feature engineering on the split data. And again, the point of cross-validation is to understand how your model will perform on unseen data. So again, the question arises, and I think you guys are skilled to answer, using the reactions button. When should we calculate our engineered features? Should we calculate the engineered features on the entire training set prior to splitting into cross-validation folds? Or should we calculate the engineered features whenever we are working on the individual analysis, so the training folds, and apply them to the assessment, so the testing folds? So is this prior to cross-validation or during cross-validation? When should we calculate the same engineered features? And back arrow for before, front arrow for after or during. No one can be suspicious now. All right, we've got a lot of votes for front arrows. front arrows. Oh, we have some vote for back arrows. But a lot of votes for front arrows. All right, so the front arrows actually have it. So it's because it's the same reason. So the point of cross-validation is just to understand how your model is going to perform on data it hasn't seen and try to reuse your data in such a way that you can get a lot of impact from it. So for that reason, since we're building models and trying to understand their generalization, we would actually want to apply the engineering of the features to the training set, the analysis set here of each fold. And then once we have the calculations that we need to understand, like something like imputation, then we would want to apply that to the test set. So let's see, if you said to yourself, wow, sounds like we are going to be doing this pre-processing a bazillion times. Like, how is that? Is that right? How is that? Well, we will. That is correct. There will be a lot of repeating this pre-processing over and over and over. However, in addition, we need to make sure that we have all of the appropriate pre-processing parameters to be able to transform the unseen data. So you just saw this, that if we're doing something like imputation on a column, that means we need to have the value that we're going to impute in the future for the unseen data. If we're doing scaling and centering, then we need to have those values that we're going to apply to the unseen data once we get it. And even further, we need to actually be able to process the unseen data in the same exact way that we do the training data. So if you have some categorical or factors that you want to one-hot encode, when you get your testing data, you would actually need to one-hot encode them the exact same way. So it sounds like you just kind of, you know me, whenever we talk about something that's going to be repeated a bunch, I'm thinking function. But here we might think about this as a recipe. Okay, so what we need is a recipe on all the pre-processing steps that we need to perform on the unseen data. We need a recipe for the things that we calculate from the training data, and we need to know how we're going to be transforming any variables that we decide to transform. The way that we can do this again is with the recipe. And you might say, Charo, that's an interesting word that you've chosen to describe this. It is an interesting word, and it's very purposeful, and you'll see why in just a moment. All right, so now we've talked about some important things about data. So we've kind of talked about the initial split and the cross-validation, but as you know, for hyperparameter tuning, it's just cross-validation again with more models. So we're kind of like through the data in the modeling part. But you can see here that actually the data and what you do with the data and the modeling, they are extremely tightly coupled. Okay, so let's look at that. So this image comes from tidymodels. And so if you were thinking that any pre-processing should be applied before actually working on the model, you might instead think of it this way. Because the model is so dependent on its inputs, and we need to make sure that our model is able to correctly generalize. So instead of doing your pre-processing outside of when you're working with the model, you want to just put them together. It'd be nice to just put them together, right? And so a great way to do that is through using something called workflow. And so the image that this book comes from is called Tidy Modeling with R by Max Kuhn, the same person who made the framework that we're going to be talking about today. And you can see here that this box, where you're doing your pre-processing, your feature engineering, and all that good stuff, is called a model workflow. So you have the pre-processing and the feature engineering, and you have it right here alongside the model. And those two things together is called the workflow. And you kind of work with them as a unit instead of working with them separately. So in Python, if you were to try to replicate this approach, there is a framework there called pipelines, and they do something very, very similar to what workflows do. However, we're going to be again working with R. So today we're going to be talking about tidymodels. And again, this framework, tidymodels, is called workflows. Okay, so let's just jump in and see how this looks in code and try and work together to understand what's going on. All right. So now we are actually going to jump into RStudio. Would you mind giving a thumbs up if you have RStudio installed, and a red X if you don't have RStudio? All right, things are looking good for RStudio. It's a win. It's a win here today. All right, well, I am going to go ahead and send out the link to the repo. And we are going to walk through how one might go about doing this. So put that in the chat. I can find my chat. Oh, there it is. So this is the repo that we're going to use. So you can go ahead and open up RStudio. You will see something slightly different looking about my RStudio. I'm using RStudio on a computing cluster at Vanderbilt called Acre because I can't run RStudio and Zoom at the same time. So you may see something that looks just a little bit different, but it will be pretty much the same user interface. All right, so let's see. I'm going to go ahead and share my screen. And again, go ahead and open up RStudio. All right, so this is RStudio as we know, and we are going to clone the repo that we're working with. One thing before we really jump into this, it could be the case that we have slightly different versions of some packages in tidymodels. So if you run into errors, just drop it into the chat, because I might have seen it before, or one of us may have seen it before. Anyway, so now we're going to clone this repo. So again, here is the repo, and the link is in the chat. As you know, we just pop over here to this code. Here we are on HTTPS. We take this, copy it to clipboard. Thank you, GitHub, for telling me that that was copied. We come back over to RStudio, and we start a new project. So to do that, we go to File, New Project. Since this is coming from GitHub, go version control. So we're going to click this one. We have a Git repository. So we're going to click this one. Now we're just going to Control V. And we can see that we've entered the repository URL here. RStudio has gave us a project directory name from the name of the repo, and it's told us where it's going to create this project. So this is a subdirectory of this root, user root. All right, so I'm just going to add this because I have one existing. You don't have to do that, but now we're just going to go ahead and create this project. All right, we are having a good life. We are switching to the project. All right, things are looking good. And we can see that we have all of the things that were in the repo here. Okay. All right. All right, and let's just take a second and catch everyone up. If you are at this point where you have your repo clone to your local directory, go ahead and give a thumbs up. If you would just otherwise, we will just repeat kind of, or if you'd like us to repeat the instructions, just throw up a red X. All right, so we are going to take 1 second and just repeat these instructions right quick to get to the repo and get it cloned locally. Okay, so make sure you have your RStudio open. Just add this back into the chat. So here is the repo link. So it's in the chat now. Go ahead and click on it, and you should be able to access it here. So this is the page that will open, and you'll be able to see the repo. So now what you're going to do is you're going to go over here to this code button and click this drop down arrow. And here under HTTPS, you're going to have the repo link. You're going to click the clipboard in order to copy it. Now it's copied to our clipboard. You're going to go back to your RStudio. And so again, mine is in a browser tab because I am on Acre. Yours should be just a completely different program. And you're going to create a new project using from the repo. Okay. So to do that, you're going to go to File. You're going to go to New Project. Oops. And we're just creating our project right from GitHub, which is a version control system. So we're going to click version control here. The kind of repository that we have is a Git repository. If you were to look at the end of the link, it would say .git. So we're going to click on this one. And then we're just going to paste the URL that we just copied to our clipboard here. So we're going to Control V it. Might be Command V on Mac, I'm not sure. And it should give you a project directory name. Otherwise, you can put one there. And then it will put it in some default location. If you want to put it somewhere else, you can click Browse and choose it. Otherwise, you can just click Create Project. And I'm not going to create project now because I have already created two now. All righty. All right, so things are looking good. I'm actually going to move this elsewhere. All right, so let's see. Now let's go ahead and open up the tidymodels workflows notebook. So let's open up this one. Oh, and just one more side note. If your RStudio looks different than mine, I have a specific theme applied to this. I look at my computer all day, and when it has like that very strong white background, hurts my eyeballs. Also, I like the color pink. There's that too. So I have just a different background, but otherwise you still have all the same kind of information here. All right, so let's get started. Okay, so first we're going to run this chunk. Don't worry okay, don't worry about it. But here you're going to install this package called Pacman. Pacman just basically allows you to load packages, and if you don't already have them installed, it'll install them for you without you having to struggle with that. So you're going to go ahead and click this button here, this green arrow. So we're going to run that one. And basically, let me just give you a quick overview of, ignore this. Sometimes you get weird errors on Acre that you guys should not see. But here are a few of the packages. So this is just the actual data that we're going to use. It's called Palmer Penguins. I love it. Tidyverse is a set of packages that help you do data processing, and it's closely tied with a package called tidymodels. Again, tidymodels is the set of packages, again, that we're using in order to do this modeling. We're also using a few helpers here. So we have use models. You'll see how this is used a little bit later, but it's going to help us generate some recipes. We also have the actual models that we're trying to use. So for example, this would be GLMNet. This is an engine for modeling linear models. And then we have this package, which is called TikTok. It's just what it sounds like. It sounds like a clock that's going to time stuff. Some of these operations are not the fastest, and sometimes you want to get an estimate on how long they're going to run. TikTok, great for this. VIP, variable importance, VIP, so it helps you with that, with plotting and calculation. We also have tidytext. Tidytext is really nice for when you have to do certain operations with text. Data Explorer, one of my favorite packages. It allows you to have like a dashboard view of all the variables that are in your data set that it can plot. And then do parallel is a way that we can parallelize the calculations for tidymodels so that things run a little bit faster. So that's what all these are. Register do parallel is just going to make sure that that actually works, this parallelization. So it sets it up for you. This one actually needs a few more statements in it, but that's okay. All right, so now let's look at the data. So just then we wanted to run this whole chunk. We clicked this right run arrow. Here we're actually going to be a little bit more nuanced a bit every once in a while. So actually here, let's just go ahead and start off by running this whole chunk so we can just see everything at one time. Let us acclimate ourselves to the Palmer penguins. All right, so here you should have some chunks that popped up, or some results that pop up. The first thing that you're going to see here is ping data. So this instruction is just, hey, load this data in and save it as ping data. Let's take a look at that. So it's here. So this is what we can expect to see in our data set. We have species, which is a factor, meaning it's categorical. Island, which is a factor, meaning it's categorical. And we have these different size descriptors for our penguins. So we have how long their bill length is, the depth of it, the flipper length, and their body mass, all numerical. We also have the sex. And so this is actually what we're going to predict. We're going to try to use all these things here in order to predict the penguin sex. Then we have year, this, but it's just an integer here. It's just in the data set. So we're going to use it for simplicity. All right, so let's look at some of the other things to build some intuition on our data. So we have this, so plot missing, plot bar, and plot histogram. These are all coming from Data Explorer. And they are absolutely super nice in terms of showing us things. So we have, this is again, what we're looking at here is the missingness of the data that is in each column. We can see that there's no missing data for these three, but we start to have a little bit of missing data for body mass, for the length of these. This tells us maybe we want to impute something for these values. And then for sex, we have some missing values where 3.2% of the data. So this tells us that we will need to drop in A's because this will be the outcome variable. And this tells us that we might want to impute. All right, otherwise, we can take a look at some things here. So these are just general distributions of your categorical variables. These are some distributions of your numerical variables. Looks like this wants to be split in half. These three, maybe this one too. But otherwise, they look okay. They don't have any like overly long tails, which might suggest that there's just some weird outlier out there or some weird value. So in general, this is looking okay. Even the scales are looking like they make sense. So we feel good about our data, and we've learned that we probably need to do a little bit of imputation on our numerical variables. We need to drop some A's. So let's do that. So now we're going to do exactly that. We are going to take this penguin's data, and what we're going to do is pipe that into drop NA, and we're going to tell it the column that we want to drop, and it's going to restore that back into ping data. So now we have a new data frame with the NAs dropped. Then we're just going to take a quick look and make sure that we have fewer rows and we have no missing. I think this is coming from Skimmer. Did I delete that? I might have deleted that. That might be problematic. We'll see in just a second. All right, and then we're going to look at the levels here. All right, so let's see. Let's try to run this. Yeah, I made a mistake there. You can either comment this out, or this function right here comes from a package called skimr. And it just kind of lets you skim over things. So if you did want to add this, just type skimr here. And here we'll see the trick of running a single line. We're just going to click here at the very end of this line or somewhere in the line. And we're just going to type Control Enter. And it's just going to run that one line. All right, that should help us out here. Maybe Control Enter. All right. So we have, okay, actually, I'm just going to run this whole thing again. All right, and we can see that we have 333 total. We have 0 missing, and we can see the levels of our outcome data, which is going to be a point. So if you work with categorical variables, be careful about the levels of your variables, and it is kind of best to kind of name them if you can. But otherwise, just make sure that you know the order of them. All right, so now let's, oh, there's a question, which is there a reason we wouldn't run do parallel? Not really that I can think of, unless you're very resource constrained. However, do parallel is kind of looking at the number of cores and the number of threads. So it might be safe to just run it kind of period. I will say about do parallel, it depends what kind of structure your OS kind of has. On Acre, for example, I can't even, like, this is currently not doing anything for me. So even though we have a bunch of cores, this is still just using the one. So if I wanted to effectively leverage parallelization, I would actually have to switch to a different package called do future, which is also built into for tidymodels use, but then I have to set up some specific ways, whether it's like cluster wise or whether it's this other type of threading. So you kind of do have to be careful about whatever you're calling here. A great way to see if this is actually working for you is just to open up your task manager and look at the cores, or just look at the processes that are there. So that's a really good question. But actually, as this stands right now, this is trying its best to just use just the one. Okay, so let's see. Great question. Okay, let's see. All right, so now let's hop into splitting the data. All right, so here we just start by setting the seed. Whenever we're trying to like build models, it'll help us sometimes to understand, in terms of reproducibility, to always be able to generate the same model over and over again. When you're just like outright trying to generate your best model ever, you could use different seeds to try to do that. Okay, so let's run set seed. See, let's just run all of these, and we'll take a look at them individually down here. So let's put this arrow. We're setting the seed here. This should sound really familiar. We've been talking about initial splits at length. This is the initial split. So now this is splitting into the training set versus the golden holdout set. And how much is being split? So it's going to put 3/4 of the data into our training set, and then 1/4 of the data into our test set. This is a really great parameter. It's called strata. It will do stratified sampling, meaning that the proportion that is in your data set, so if there were like 10 female penguins and like 1,000 male penguins, that would be reflected in each of the splits. Okie dokie. Let's see. And then we've also applied a function called training, which extracts the training set out of this object, and then the testing function, which extracts the testing data out of this object. So then let's see what we've been looking at here. So we have, let's type in data split here, just so we can see what that is. So it looks like this. This is why we have this training and testing thing, because it's not really, this is not really helping us to look at. So let's look at the training data. And can you all actually see my screen? Maybe I need to make this a little bit bigger. There we go. Not maybe a little bigger. Too big. That's okay. All right. So I'm just going to control enter this one. Look at some of the training data. We can see that we have fewer pieces of data in our training data than the entire data set now. But we can see that we have data. We can see that we have different values here. So it's not like this repeating thing. We have an appropriate training set. You can also look at our test data. And again, what I just did, click here, control enter, which runs just the one line. So now we're looking at 84 rows, and we can see them here. So now initial split, done. And we have our training data and our test data, which we will never look at until never. Okay, so let's see. Yes, so in missing, yes, I made a mistake there. If you want in missing to work for you, then what you would need to do is come back up here to your pacman p load statement. Thanks, Miguel. Beautiful. You need to add the skimmer package, which I forgot to do. And then you should be set. All right, so now we have golden holdout train. Now it is time to try the feature engineering. Okay, so now we're going to start with our recipe. So there is a really great package that I just told you about called Use Models. Use Models is going to help you to generate a template for tidymodels. So everything you need, the recipe, the model specification, and then putting that together. So the workflow. So it's going to help you. So let's see what that looks like. All right, let's run this. What is this, by the way? So this is the function out of Use Models to generate a GLMnet. And this whole thing right here is a formula, which is going to say, hey, what's the outcome variable? For us, it's sex. And we understand that it's a formula based on all of the other values in the training set. That's what this dot means. Everything here, species, island, billing, all these things other than the outcome variable, which is sex. How does it know what data set we're talking about at all? We tell it that the data that we're using is the training data. And that allows it to know what this dot is and to understand this variable sex. So let's just run this. We're gonna arrow this one. Fun. All right. So now things are all coming together, right? So we have this GLMnet recipe, where we're talking about the things that we need to do to our data. So this is the same formula, right, that we just wrote. So this is telling us what we need, the data that we're going to be operating on. It's also telling us what are the predictors. It's also telling us what are the outcome variables. Then you have these steps. So this is kind of the base like object for the recipe and tells you about the data. But then there are the steps that you apply things or operations, transforms, anything you need to do to the data. And each step has a particular kind of operation. So step novel does something in particular, step dummy does something in particular, step CV does something in particular, and step normalize. So step novel is going to look at your data and see if there's anything that hasn't been in the data set. So I think this really is more important for the prediction. You have step dummy, which is going to take your categorical variables and turn them into dummy variables. So instead of being like cat, dog, rat, it's going to be like is rat 1, is cat 0. So it's just going to turn things into dummy variables. And if you don't know what dummy variables are, you can just read more about that. Step ZV is going to remove variables that have 0 variance. So let's say, like, for some reason, you have a column that is literally all the same values the whole way down. Why do we need that? Cut it out. Step ZV is going to do that for you. And then you have step normalize, which is going to do the normalization. So this is the recipe, okay, that's going to be applied every single time that you need to work on a subset of the data. So even though this says data equals trained data, this is more like a recipe for what you can expect to see in the data. All right, so we talked about what these different steps are and that they exist. But what are these other things here? Like what is this? So this tells us what these steps will be applied to. So maybe you don't want to apply step dummy to a numerical variable because, that doesn't even make sense. So you would need to tell it what variables you want to apply it to. And the way that you can do that is through using these tidy selectors. Is that what they're called? Yeah, tidy select selectors. And this right here just means, hey, look at my entire data set. Everything that you saw that was like a factor and wasn't numeric, apply that to every single one. Apply the step dummy to every single one of those. Except, that's what this minus means, anything that's an outcome variable. Don't step dummy any of my outcome variables, but if it's a predictor, do all of those. So you can see those here. So we have step nominal for all nominal, step not all nominal for step dummy. For 0 variance, we might want to just do it on all predictors. So if we have a numerical column or a categorical column and it has all the same values, we don't want it regardless. For step normalize, we do something similar. So we do all predictors. So all predictors minus the ones that are nominal, because we need to do it on numerical variables. As it were, there have been some changes to tidymodels that have helped us to kind of phrase this in an easier way, and we'll look at that in just a moment. And you can see here that we have a specification for a model, right? You can see this thing that says logistic reg. Sounds like a model. GLMnet, that sounds like the engine that we just said for use models. Mode, that sounds like what we're doing. The workflow. Interesting. So we said before that we wanted to package the data and the data processing and the model together. And that's precisely what this is. So you make this blank workflow and you add the recipe that you want. So that would be this recipe. So that's what we're going to apply to the data. And then we also have where we're adding the model. So now it's all packaged up into this thing called a workflow. We'll come back to these two things in just a moment. So as it were, what you could do is just take this, copy it all, put it down, and you'd be 98% of the way there. We are just going to roll this back a little bit because we are not actually going to do this tuning grid just right now. We'll come back to that in just a second. So that's what these last two things are. They're about establishing the hyperparameter sets that you would want to use during training. And then this is going to actually do the hyperparameter tuning on your resamples. So do keep in mind that you would need to fill this in, and we'll see how you can do that. All right, so again, what you could do here is just copy and paste this. I put this recipe here so that you would be able to see like the newer way that tidymodels allows you to specify predictors and variables that you want to provide to your steps. So before, we had all nominal minus outcomes. What is that actually? I just mean all nominal predictors, right? So now tidymodels has a selector, which allows you to put that just directly in all nominal predictors. And so that here we have that. Here we also added this step, which is going to be imputing the mean. So we're going to do that again for all numeric predictors. Otherwise, we're just going to keep everything the same. So keep in mind, although use models gives you like this template, you do what you want. Add the steps that you think are important. So I'm going to run this. So again, Control Enter. It's running all that. You can see now I have the GlimNet recipe. Now something is interesting that can allow you to have some insight into what's going on with your models is to actually look at this. So here is like the variable in our global environment. I'm looking at this under the environment tab. I can really just jump in and see what's going on here and what the recipe is doing. Oops. But we can also just look at the recipe here. So here, I'm just going to type in GlimNet recipe. I'm going to type Control Enter, and that's going to show me the recipe. All right, so let's look at it. I'm looking at the first one here. Interesting. No inputs. Wonder why that is. I also wonder if we've actually applied this to anything yet. We'll see. We also have the operations here. And so we can see all the things that are going to be applied to each of our different data sets. Okay. So we can see the descriptions as well. Novel factor level assignment, adding dummy variables, doing mean imputation, adding a zero variance filter, and doing centering and scaling. And we can see what we're applying that to. Also, we can see just kind of a summary of the types of data that we have, which are called roles. It's saying, look, for your model, it looks like you have 7 predictor variables and you have 1 outcome variable. If you look further at tidymodels, it will allow you to specify different role types. If you also would like, you could look at the summary. So we just type summary of the object that we're interested in, which is going to be GlimNet recipe, Control Enter, and we can see here completely what's going on. So we have exactly how things are categorized, what is a numeric, what is a nominal, and what are the roles. So that's really nice. It gives us good insight into what's going on, and it allows us to confirm our expectations, which is very important in data science. Or refute, confirm or refute. We just need to make sure that what we expect is either done or not, and if we need to fix it. All right, so now we have the data part of our workflow. Let's talk about the model part. So our models are coming from Parsnip. You tend to use, I think it's required that you use Parsnip models with tidymodels. And here we're just going to test out a logistic regression, which is a method of classification, which can be used for classification. We can see this here. Strongly used for that. So here's the actual model that we're using. Yes, nominal is just going to be something that's in name only. So like It's not really a like a numerical, like integer double float. It's going to be like a categorical or factor. Okay, so this is the model that we are applying. It's logistic regression. And often there are parameters, hyperparameters that we were talking about, that we need to set so that the model knows like what values do I put here. I don't know, I can't calculate them. So I need you to tell me what these values should be. One of these values in a logistic regression is going to be the penalty. And so here we're just going to specify a number for it. We're going to give it our best guess based on nothing in particular. It's just a number we're using. Then we're going to set the mode for our model, which is going to be classification. And then we're going to set the engine. So this is how the package that we're using to compute GMT20210804. So now let's just run this, see what we get. Wonderful. What if we looked at this? Would it provide us any insight? Let's see. It's going to type GMT20210804. Just the name of our object. Clearly there are some issues with my typing. Wow, that wasn't really overly helpful, but it kind of is in the sense it tells us exactly what we're doing, the main arguments that we have, and the engine that we're using. This will come back up. So something that is really awesome is we just had to actually have a lot of knowledge to be able to write these lines. Like we had to know what parameters were available. We needed to know like how we were going to set the mode and if we needed to. And we also really needed to know the types of models that are available through tidymodels. All right, so there's a way to get around this provided by Parsnip, which is so awesome. And I'm very excited to show you this today. I've commented it out, but actually uncomment this line. Parsnip add-in. So this is a function that is provided through tidymodels, and it actually is an add-in to RStudio, and this will make that happen and also load it for you. So this is like so exciting to me. One thing that you should take note of is it's starting the server to operate this function. So if you try to run anything else in here while this is running, it will not run. So you need to click done here to finish out this operation, and then you can get back to your R part. So now let's take a look. Okay. So we're doing classification. These are all the classification models that we have available. Okay. So we have lots of different like bagging, we have boosting trees, we have different engines for them, we have decision, we have different types of regression, we have discriminating functions. So that's going to be like your Bayes-like things. It's just very exciting. All of it is very exciting. So if you wanted to pick something else, you could do this here. So here we're just picking classification. This button right here is quite interesting. So when we get to hyperparameter tuning, this is going to be a big deal. You can unclick this for now, but there's still like amount of knowledge that you have that you need to have to be able to set the required parameters. So we'll come back to this, but do know that if you need to find a model or you're interested in certain models, this can help you out. Last point. Let's go down to GMT, logistic red. So logistic regression. Let's just click enter here on the GMT. Beautiful. You can write the specification code. Let's see what happens. It added it right here. And then we can click done. You can see that it terminates and it's ready to move on with my R stuff. So this is what it added in just then. You can see here that it says this penalty equals tune. Interesting. Mixture equals tune. Interesting. That comes from the checkbox that I had, which is add in like tunable parameters. But again, we'll come back to this. Go ahead and delete that for now. And I'm just going to comment this out in case I'm running again. Now, did I run? Yeah. All right. So now we're almost there, right? So we have recipe and we have the model that we want to generate with some of the type of parameters set. So we said before that when we have a workflow, the workflow is composed of a recipe and then it's composed of a model. So we need to add to the workflow the actual recipe of the model to compose the workflow. So let's see, how would that look? Well, we just kind of said the words there. So we need to add the recipe. I wonder if there's a function that does that. Let's see, add, oh, goodness, there it is. Add recipe. It says we need to add first the original workflow, and then we need to add the recipe. No problem. We've typed in that original workflow, and now we're going to add the recipe. What was the recipe we had again? Limnet recipe. Perfect. And now we also need to add the model specification. I'm going to do that here. Wonder what the word is for this one, or the function is for this one. Could it possibly be add? Oh my goodness, it is add models. Add model. And now what are we going to do? Add the specification as it says, which is our Limnet spec. All right, so let's run this. By the way, just then I typed Control-Shift-Enter. Sorry, I use a lot of shortcuts because I just need to go. So otherwise, we could have again clicked the arrow. Same thing. So we can also again look at this. Might not be the most illuminating thing, but let's see. Let's see what this object looks like. Interesting, interesting, interesting. So we've learned something here. Our workflow is composed of this preprocessor, which is the recipe, and our modeling, which is logistic regression. However, it also talks about this, what the steps are, all the steps for the recipe, and the model itself. So now that we can clearly see our workflow is this package deal of the pre-processing with the model itself. All right, now let's see how we can use this. So here we are again. We're just gonna straight do cross-validation. Like, it's difficult for me to conceive of not doing cross-validation. So we're gonna use a specific method of cross-validation here. So this is called vfold CV. So this is k-fold cross-validation, but here's denoted with the V. We're gonna pass in our training data. So this is what we wanna split up into K or V folds. And we're again going to stratify on sex. So this is looking incredibly close to our initial split because it is very similar to our initial split. It is just a resample. So after we actually split into these folds, we are going to look at what the splits look like. And then we're going to look at a specific split. So let's run this one. Alrighty, so this is what the splits look like. How many folds or splits did we ask it for? 5. So 1, 2, 3, 4, 5. And then if we were to look at one split, what is this? Intéressant. It says row and data, and the row are not, like, these values are not one after another sequential. So we can see what this is. So these are the individual rows of the training set, which are in this particular split. And this labels what split they're in. So this is in the analysis or the training set. If we were to go further over, we would see some things that are in the assessment set. So if you ever need to snatch these out of your data again, you know just what to do. You can use the splits. All right. Let me see. It looks like there's some questions here. I would hope that that's it. Sorry, you guys might have to ask that again. All right, so, oh, you ready? Okay, good.
No, I was just gonna say it's not terribly important. We can move on.
Okay, okay, sounds good. All right, so now that we have our cross-validation folds, let's do some cross-validation. So we are going to do that. Let's see, so this is the Lim network so that we had bundled that together, right? And then we are going to call this function called fit resamples, which is going to do a fit over all the resamples, but it also needs to know what the resamples are. So we're going to pass in the CV folds that we just made here. This is going to give us the results of the fitting the resamples. So right after that, I'm just going to go ahead and type in CV results here so we can look at them afterwards. This slide here, okay, we'll come back to that. So actually, I'm just going to run this one alone. So I'm going to run this, Control-Enter. All right, so we see that I have my arrow back, which means it's completed. I'm going to click on this one so I can view what this looks like. Control-Enter. it shows here because this is an HTML notebook. Wow, this is not the most helpful thing I've ever seen, but I understand that the data is here. The way that we can approach this is if we wanted to see the metrics. So what this is the results, right? So this is fold 1, or these are the folds. And for each of the folds, it tells you all the data that's in the splits. It tells you all of the metrics for each of the folds and whatever notes are available about them. So if they failed or whatever reason. The way that we can approach fixing this is a tibble. What we want to do is do something called unnesting. So we're just going to grab the columns that we care about. Maybe we don't care about the splits as much. And we're going to unnest at least the metrics. So this is what this does. It's selecting the fold ID alongside metrics and notes, selecting these particular columns. And then it's looking at metrics and it's going to unnest it. All right, what does that mean? Let's see. Let's see what that does. So now we can feel like we're looking at something. Okay, so now we have each of the folds, right? 1, 2, 3, 4, so forth. And we have each of the metrics that we decided to look for. Sounds weird, huh? You don't remember specifying any metrics, do you? Interesting. So that's a consequence of fit resamples. There are parameters here that are default, which say, hey, do ROC, AUC, and accuracy. However, of course, you can pass in some different things that you want to calculate on. So just real quick, if you type in question mark, fit resamples, click enter. This comes from Tune. So it's also in workflow sets, but it came from Tune, which is now in workflow sets. So let's click this one. So we can learn here, oh, that's interesting. Metrics, interesting. So this is how we got those standard set of metrics because it's null by default. Anyways, so here we can see that we have some different performances on each of the folds. If we wanted to plot this, this would be a great way to do it. But we can see that we have the metric, the fold, and the value of that metric. So this is long data, which is awesome. So for basically fold 1, the accuracy is 0.92. For ROC AUC, it's 0.98. And we go such and such, so forth for each of the folds. All right, let's see. This is the one we just ran. So there's also a really great function in tidymodels called collect metrics. What that does is it allows you to see how the model performed over all of the folds. So how it performed in aggregate. So let's see, let's run. So I'm going to take this, I'm going to highlight both of these. Control enter. That's going to run both. Up. All right, let's see the results of this. And so here we can see the aggregated results for each of the models. So this is one model, but we have 2 metrics. And we can see it aggregate over the folds how well it did. So it's doing pretty well. Looking good. And we can see the number of folds as well. All right, so now we have our cross-validation metrics. We feel really good about ourselves. But now what we have are 5 models if we chose to keep them. Now we need 1 model built on the training set. And we can expect similar performance of this. So let's see how we can do that. So now that we have our workflow, which we already had, by the way, now we can actually fit on the full entirety of the training data. And we're just going to resave this into a separate model or a separate object called limited workflow final. And we're going to look at that. All right. So I'm just going to do this one. So we're going to do this arrow. Might take just a little bit more of a second. All right, here we have here. So let me just see something right quick. So here, this is when we were looking at the workflow before, right? You can see here it just says workflow. Okay, good to know. But here, after we've trained the workflow, we see something interesting. And we can see that this is a trained workflow. So now it has values fit to it. And this is the model itself. We didn't have that before. We have a full description of the model with some extra things here. So now we've learned about the model, we have the recipe steps, and we know that this is trained. So do we look at this a lot? No, we tend to go to these things when we have issues. All right, so you can also predict with the model, obviously, because that's kind of what it's for. And the way that we can do that is we're going to use this final workflow that's been trained, right? And so GlimNet workflow final. Sorry, I'm making all seasick because I have some real scrolling going on.
Oh, and I think Miguel had a question.
Oh, sorry. What is the accuracy that we're measuring and taking the mean of the model run on the fold? What a good question. So here, this would be the performance of the model. So this is the mean performance of this particular model across all of the folds. And the accuracy. So let me answer that in just a second. So let's try to predict so we can see where what these metrics are calculated on. So these are calculated, like this is calculated using the final fit, but the same thing would have been done during cross-validation on each of the workflows that were fit. So what we're trying to do here is we're going to predict. So we're going to use our workflow, and before on our cross-validation metrics, we would have fit to a particular cross-validation fold. And we're going to predict on the training data. So now we're back testing. So after that, what we're going to do is we're going to bind the probabilities onto these predictions. So this predict function is only going to tell you the class that's predicted. But if you want to get the probabilities associated with that prediction, you need to use this type equals prob argument. And then we're just going to bind columns so that we also get the true values onto them. So let's see what this looks like. So we're going to run that. Then I'm just going to add GlimNet training pred, because that's what this object is called. And we're going to control enter that, see what's up. Okay. So you're talking about accuracy. For each of the folds, you would have had a prediction that looks just like this, right? So you have the predicted class and you have the actual sex for your assessment set. So when you're talking about accuracy, you're talking about, okay, how many of these match how many of these out of the total? When you're talking about AUC, ROC, AUC, you're talking about a calculation done for over these. So whether pred female or pred male, whichever one you're interested in. And it's actually going to use the 0 as level, which is why we looked at the levels in the first place. Okay, so that is what those values are. We would have done this for every single one of the folds. So we have fold 1, we got the accuracy based on that one. We did fold 2, got the accuracy based on that one. Fold 3, accuracy, 4, accuracy, 5, accuracy. 5 different accuracies. Then if we want to collect the metrics, we took the mean of that, and now we have 1 accuracy for that model. Yeah, it's doing like crazy good. We're all like amazing data scientists. It's doing crazy good. Okay, so now we can also do some computations on this. This function right here is actually coming from yardstick, ROC, AUC, and so this is just going to plot this column in the data set with the probabilities that are coming from pred female. So let's look at that. Oh, sorry, it's not plotting. There's an auto plot function for that. We'll get there. So here we can see the estimate there. Again, it's doing very, very well on the training data. We also saw, however, that it was doing pretty well in the cross-validation. So that's a really, really good sign about the performance of our. This is about 92% accurate. I don't remember the actual training or the class balance, but we may not actually be doing very well to be looking at accuracy here. But just looking at the ROC, AUC, it's looking okay. So again, like the default metrics are going to be accuracy and ROC, AUC, but we can add in other metrics that might be more appropriate for our model. So like the F measure, F1, F2, sensitivity, specificity, and we get to put in a whole big old giant list of all the metrics that we want to see after we're done training. So I am running a little bit behind, a lot behind. And we have a little section where you can try some things out yourself. So in the interest of getting to hyperparameter tuning, because I know there are some people that are very interested in that, this is something that you should for sure try at home on your own. So this is some insight into the use of tidymodels. I gave some very specific examples of like 3 or 4 specific functions that you can use, but there are tons of functions in tidymodels that can help you out. So these kind of give some insight into some things that you can find. So for example, recipes, there are so many different types of steps that you can apply to your data. Take a look at the ones that are there. Take a look at some of the different models that are available for both classification and regression. Take a look at some of the different types of engines that are available for those things too. We here did k-fold cross-validation, but there are lots of different types of validations that you can do. There's bootstrap resampling, Monte Carlo, you can make your own sets, whatever is appropriate to your situation. Also, take a look at the tune package and yardstick. These are going to help you to add the metrics that you want in the correct way, and also learn a little bit more about the things that are available to the tune. So I'm just going to take a few minutes here, and we're going to speed through hyperparameter tuning. Okay, don't worry. Don't worry. Don't worry yourself. So here, things are going to look very, very similar. That's why I said don't worry. So here we have the same logistic regression that we had, right? Except now, instead of putting a specific penalty, we're putting this placeholder that basically says, I don't have any idea what this value should be. Maybe I have a slight value, a slight idea, or I have a range, but I don't know the exact value. If you could look at that for me, I would appreciate it. It's a placeholder here that tells tidymodels exactly that. And since there are 2 parameters that are available, at least 2 in GLMNet, then we can do that for both parameters. So otherwise, this is looking the exact same. We don't really need to change the recipe because we have it just how we want. So we can take our original workflow that we had, and we can change out the model specification. And so here we're doing update model. That means we're just putting in this new specification right in place of the old one. All right, so let's see. Just going to run this one straight. You can see the change here. Again, this is not trained. We work back to the original one. And also you can see the arguments here. Before we had penalty equals 1, e -3. Now we just have specifically tune. So that's telling the tune package something that we're going to try and learn something about these. After that, we just define the parameters that we want to be able to tune. So the workflow already knows it. We grab it out of the specification, and then we make this grid. I think these grids come from dials. There's different ways to make the grids. But what is a grid? It's just taking the parameters that you have. So we have mixture and we have penalty. And we're saying, all right, I want a grid of size 5. So give me some combinations of these values based on the defaults that would maximize the entropy. And so that's going to be our grid. We can actually take a look at this and see what's going on. All right, so we see 5 combinations of penalty and mixture, and it's going to do that in order to maximize entropy. Again, with dials, there's lots of different grids that you can use, or you can define your own. And so when you saw use models before, they defined their own specific combination of these hyperparameters. All right, so this is the grid. Now, all that's left is to trade over the grid, right? So we're taking that same workflow. We're piping it into this function called tune grid. That sounds like we're tuning this model, those tune parameters over the grid that we specified. So now we tend to do cross-validation. So just like we said, for our resamples, we're fitting the resamples. So this is the same cross-validation fold that we had before. But now we're adding this grid, which is defining the sets of hyperparameters that we want to use. This is how you can actually add in a bunch of other different metrics. So there's many of them, but there are also more that are available through Yardstick. And this is also giving us some insight into, so this control is giving us some insight into the performance of the model. There are lots of other different parameters, as you can see here, that popped up about the way that you can have some insight into the way things are tuning. So I am going to run this. As you can see, it's wrapped in tick and talk. So we'll be able to see how fast it runs. It's possible that we may have to end this workshop before it's done running. Baker has been friendly lately though, so we'll see. Oh, took 3 seconds. Gorgeous. So now we have our tune grid back. So first, let's take a look at what that is, what it looks like. Here we have that same sort of thing again, where we have these nested parameters. We're just going to take our tune grid, do the same thing that we did before, unnest it. So I'm going to highlight that, Control Enter. This is giving us back GlimNet fold metrics. What I'm actually going to do is I'm going to open this up in a viewer so we can see a little bit more of what's going on. So I'm going to click on the name of the variable here in my global environment. And here we see many things. All right, so again, we have the fold number, right? So this is all the behaviors on the first fold. Out of this first fold, we have a lot of metrics that we define. So this is one set of results on one particular fold for one particular model. So here goes that one model right here, model 1. Here goes model 2. This is the same model, but defined by a different set of hyperparameters. So now it's called a different model, but it's its performance again on fold 1, and here are all the metrics. You can see something similar for all of the different models on all of the different folds. Okay, and so now we're a little bit out of time, but I would encourage you to look through the rest of this notebook. What you'll see here is some plotting functions that are like able to be applied. There's also ways to collect metrics. So again, this is going to be collecting the metrics across the different hyperparameter, so across the different models, and you can see how well that they do. And here we go. Get back there. You can see that this is the model 1 again, model 2. So this is comparing how well each of the different hyperparameter models do. You can select the best one, and then you can fit the model on that best set of hyperparameters. So this is a really great workflow for if you need, so if you've seen that your model seems to be doing like kind of okay after cross-validation, and you're trying to pick the one that's good. Trying to think if there's anything I also have to say for this, but I think this is most of it. Again, please go through the rest of this notebook and see some of the other things that you can do with the IP. And again, jump on tidymodels, give their API reference a look. Make sure you click on all of their little honeycombs so you can see their different packages that they have available. Otherwise, thank you so much for coming. I always love talking about tidymodels. It's been really effective in the work that we've done at the DSI. So I'll be here for a few minutes after if you have questions. Thanks for coming.
I have a quick question.
Yeah.
So if I don't know what I'm doing at all with the hyperparameter tuning and I don't know how to set it, would you say then the best approach would be to try to run one of those like preset things from the use models package and see what sort of tuning they have for that type of model? And then a related,
go ahead.
I was gonna say, and then a related question is, is it like very comprehensive? Like, do they basically have a use model preset for almost everything that's in tidymodels?
Do they have a use models? That I'm not sure about.
Okay.
But the actual grids are using some default values. Like the grids from dials, like the max entropy and all that good stuff. All you're actually telling them is how many combinations that you want. So I think they're already set off of some predetermined like values, which could be helpful in just starting with that.
Wait, so okay, so if I change